Now let's look at one detailed numerical that is helping us to understand the Monte Carlo simulation, especially combining both inverse transform method as well as accept reject method. Right? It helps us in terms of understanding both of them quite comfortably. Let's try that out. The truncated exponential distribution on the interval 0 comma c is defined by the probability density function f of x equal to a e power minus lambda x. Lambda is a parameter, a is a constant. Now this is an exponential distribution, right? So derive an expression for a in terms of lambda and c. Now because this is an exponential distribution, all we are saying is the probability density function over this entire range, integrating the probability density function over this entire range should result in a summation equal to 1. So doing that, a times e power minus lambda x by minus lambda, this getting integrated between c and 0, this should be equal to 1. So minus a by lambda times e power minus c lambda minus 1 is equal to 1. So as good as a by lambda times 1 minus e power minus c lambda, this is equal to 1. So from here I can very well find out my a, which will go as lambda divided by 1 minus e power minus c lambda. So this part I am able to achieve. The value of a is lambda divided by 1 minus e power minus c lambda. Alright? Okay, that is the first part. Then look at the second. Construct an algorithm for generating the samples from this distribution. Okay, now for this I have to generate samples from this distribution using the inverse transform method. So we know now f of x is equal to a e power minus lambda x, or probably a better way to talk of is a, because a is lambda divided by 1 minus e power minus c lambda times e power minus lambda x. Now inverse transform method requires me first of all to come out with the capital F of x, which is the cumulative distribution function. Right? So for this, if I want to find out the cumulative distribution function, I am integrating it between 0 to x, a e power minus lambda y dy. A will substitute it later. So it is as good as a times e power minus lambda y by minus lambda, substitute x and 0 here. So which is giving me a by lambda times 1 minus e power minus lambda x. And now a we already have, right? A is lambda divided by 1 minus. So lambda go up. So finally f of x, which is the cumulative distribution function, is coming out as 1 minus e power minus lambda x divided by 1 minus e power minus c lambda. This is what is the cumulative distribution function. Now for generating the random sample, what is the process for us? Once I have this distribution function, right, I will have to find it out the inverse of this. So let me take some u equal to, which is f of x, capital F of x. So I'll take it as 1 minus e power minus lambda x divided by 1 minus e power minus lambda c. Now this is from where I try to find out my x. So I can simplify it 1 minus e power minus lambda x equal to u times 1 minus e power minus lambda c, right? And from here again e power minus lambda x is equal to 1 minus u times 1 minus e power minus lambda c. Minus lambda x is going to be the logarithm of 1 minus u times 1 minus e power minus lambda c, and obviously x is coming out as minus 1 by lambda times logarithm of 1 minus u times 1 minus e power minus lambda c. Now this is what is the value of x. Right? So when I am generating for some values of x, lambda and c, right? Let's say if I am taking, now let's say let me try to generate it. Right, now let me take a few random numbers. Right, let me talk about a few random numbers u, which are pulled out from 0 comma 1 kind of a distribution. I'm pulling a few random numbers from a uniform distribution. Let's say these are some of the random numbers that I have pulled out. Now here let me assume for simplicity purpose c value is 1 and lambda value is 2. Just for the sake of assuming, I have taken in this distribution the c value is 1 and lambda value is 2 because both are constants. So what I am planning to do now, x is going to get generated for this particular distribution. Okay, if I freeze out all these random samples, right, these are the different random samples I am freezing. Now I am computing the x minus 1 by lambda times logarithm of 1 minus u times, this is u times 1 minus e power minus c lambda, 1 minus e power minus c times lambda. Now this is what, right, u times 1 minus e power minus c lambda, I am talking of this number. So from x there is a distribution that is coming out which is doing minus 1 by lambda times log of 1 minus all that stuff. Now the x is coming out to these particular values. So the distribution of x from the uniform random distribution like this, I'm finding out the values of x which are working out to these kind of numbers. So this is the way we are generating the samples from the distribution using the inverse transform method. Now here if the lambda is coming out to be 2 and c is coming out to be 1 for this particular. Now if I am changing the c and lambda, if I am changing c equal to 20 and probably lambda equal to 10, I get completely different set of values. Or probably if I am making lambda equal to 0.5, I am getting a completely different set of values. Here these are random numbers, but these are the values that are getting generated from the corresponding distribution of x. That's how we typically operate. Now, the other important part is, suppose that 0 is less than lambda is less than c. Now lambda is lying between 0 and c. Consider the truncated normal distribution defined by the probability density function. I am looking at g of x, which is a probability density function which is being looked at as e power minus x squared by 2 divided by square root of 2 pi times phi of c minus 0.5. Right? Okay, this is the probability density function where 0 is less than x less than c. So where phi is the cumulative density, extend the algorithm in 2 to use the samples generated from f of x to produce the samples. So this is where I am using the samples that are generated from f of x to see whether I can use them for g of x or not using the inverse transform method. Now, how does this inverse transform method works? Okay, I have to depend on f of x along with for generating the samples for g of x. So for that, the objective for me is first find some m, which is nothing but the maximum of g of x divided by f of x. I have to find out the maximum value of g of x divided by f of x. So which means I have to find the maximum of, okay, g of x is e power minus x squared by 2 divided by square root of 2 pi times some phi of c minus 0.5. Simplified. Okay, this part is constant, so I'll not bother about it. This part is constant, I'll not bother about it. So at least g of x for me is e power minus x squared by 2. And what about f of x? F of x is a e power minus lambda x. And what is the value of lambda for me? What is the value of a for me? A is nothing but lambda divided by 1 minus e power minus c lambda. Right? So the same thing, if we are taking it up, it is nothing but, probably I can even take this out saying this is a constant. I can even omit this. So basically it's coming out, right? Even this part is coming out to be a constant, so I'll ignore. So I'll take g of x divided by f of x, which is nothing but e power minus x squared by 2 divided by e power minus lambda x, which is in a way working out as e power minus x squared by 2 plus lambda x. Now this is the function, okay, I want to look at this particular function m, which is going to maximize this. So it's as good as, I will try to maximize, the rest is a constant, so I will try to maximize e power minus x squared by 2 plus lambda x. After that I will try to find the value of m. So if I have to maximize it, probably let me call this as h of x. So that's where I am trying to do h dash of x, the first derivative of it, and trying to equate it to 0. Okay, this times, what is the derivative of this? Minus x plus lambda. Now if I am equating this entire derivative to 0, it's as good as x equal to lambda. Right? And is it a maximum? I have to take the second derivative and check it out. The second derivative is giving me a negative value because this is e to the power of something minus of this minus 1, which is a negative. So I can very well take that the maximum is occurring when x equal to lambda. Okay, the maximum is occurring when x equal to lambda. Now what is that maximum value? If I have to compute that maximum value, I should definitely require the whole expansion of g of x by f of x. What is g of x for me? E power minus x squared by 2 divided by square root of 2 pi times phi of c minus 0.5, and by f of x, a e power minus lambda x. So a is already known, lambda by 1 minus e power minus lambda, e power minus lambda x, probably here it is going out to e power plus lambda x. Now I'll substitute x equal to lambda. So right, that is where the maximum is coming out, which means it is nothing but e power minus lambda squared by 2 plus lambda squared. So e power lambda squared by 2 times 1 minus e power minus c lambda divided by lambda times square root of 2 pi times pi of c minus 0.5. This is the typical value of m. Now, once I have the value of m, I can very well find out. Once I have the value of m, I'll try to find out some v, which is nothing but g of x divided by m times f of x. So this number, okay, this is my m now, which is the maximum value of g of x times f of x. This multiplied by, right, I have to have this in the denominator, g of x into f of x divided by g of x divided by f of x by this. So which means overall, if I am looking at, this is getting stuck off, right? This part is getting stuck off, this part is getting stuck off, this is getting stuck off. So overall it is remaining e power minus x squared by 2 plus lambda x minus lambda squared by 2. This is what is the value that is coming out for v. Now, this is where we'll use the accept reject kind of a criteria. Now that we have already generated the values of x from here, I will have to check out for this particular value of v. Right, I will check out for this particular value of v based on the lambda e to the power of minus of x squared by 2. Okay, I'll find out the values of v in each of the case. E to the power of minus of x squared, this is x squared by 2 minus x squared by 2 plus lambda x, lambda times x minus lambda squared by 2 minus lambda squared by 2. So I am trying to find the value out here. For different possibilities, I have taken the value. Now, this is where I am using this accept reject, right? And probably I can very well use either this, or probably I can generate a completely different set of random values. I will not depend on this, right? Probably we have generated x, and again based on a random sample whatever we had, I am generating v. And if at all I am seeing, so when I am talking about whether x has to be returned or not, right, the sample wise what I am typically seeing is, if at all v is, if at all whatever is the v, here we are generating v from so here if I am generating, okay, this is the computation which is e to the power of minus x squared. So this is the computation value. Now v we are generating from again a random uniform random sample. So let's say I am generating these as my v's. Now what I simply say is, if my v is less than, now accept reject kind of a sample. Now if I really want, now if these are my v's, as long as my v, right, this is where I'll check the accept versus reject kind of stuff. If my v is less than whatever is the calculated value, I'll keep it, I'll retain it, which means I'll return the value of x right? I am returning the value as X, otherwise I am going off, right? As long as I am seeing the random number that got generated, now I'm generating V. Okay, now that I have the X, which is computed from based on these values. Now these are the X's that I had. Using these X's, let's say I have computed these as my values, and whenever I am seeing the value of V here, if the value of V is lesser than that of this computed, I am returning the X as the random sample, otherwise I am going ahead. So V is generated from this U, and if at all I am seeing V is less than this calculated value, I am returning X, where otherwise I am just ignoring. So which means the random values which I am generating, out of this I am ignoring these 3 random values, and rest of them I am taking because they are still adhering to this kind of a distribution. So that's how I can use the accept reject criteria to typically arrive at the computations from one set of random variables. So that is how we use both the inverse transform method as well as accept rejection method to finally arrive at the arrive at generating the samples from a specific distribution. All right.